Hello, and welcome to the presentation video of our final project for ECE 549. Our project's name is HAODE-Net, which stands for Hazy Object Detection. We aim to do object detection in hazy environment with high accuracy and robustness. Object detection has been extensively studied in recent literature. There are many off-the-shelf models available with high accuracy and robustness on clear images. However, it is still facing the bottleneck of adverse weather conditions, like haze and rain, as they jeopardize the quality of the images greatly. In this project, our goal is to train an object detector that predicts objects and classifies accurately in hazy environments. The input are only the hazy images, and the outputs including the bounding boxes coordinates and the confidence scores.
To solve this problem, the most naive approach is to run the object detector on the output of an image dehazer. However, this method is slow and not ideal for real-time performance because a good image dehazer is also quite computationally expensive. Therefore, we initially formulate our problem as to make the detector to directly operate on clear and sharp image features instead of the ones extracted from the hazy images. And to accomplish this goal, we initially tried the idea of multitask learning. So as shown in this architecture diagram, we add another output head to the backbone of the SSD. So this is a dehazing branch that operates on the same set of features and generate a clear image. So we assume that the model can also have a sense of what the clear image features look like. Also, in some of the other literature works, the multitask learning is proved to act as a regularizer, making the network to achieve a more generalized set of features. Therefore, during the training process, we jointly optimize over two tasks. And we introduce a hyperparameter called lambda to balance the ratio of these two tasks as shown in this loss function. In our experiment, we use a lambda of value 0.1. So basically, we focus more on the detection and only use this dehazing branch to help the detection output. However, the vanilla multitask learning approach has some problems. Our dataset does not have access to both hazy images and the corresponding ground truth clear images.
To relax the requirements and compensate for the missing dataset, we proposed two more methods. The first one is continual learning, and the second one is multitask learning with knowledge distillation. First, I would like to introduce the continual learning approach. Continual learning was originally proposed to improve the ability of models to solve new problems without forgetting the previous acquired knowledge. In our case, we want our model to learn detection knowledge without forgetting the dehazing knowledge, and vice versa. We are going to implement this approach using gradient episodic memory, which indicates that for every new training data, we're going to update the parameter in a way that it will not increase the loss of the previous training data. The pro side of continual learning is that now we can separate the training set for detection and dehazing tasks, which solves the missing dataset problem. But the con side is, since we are going to save all the inputs to the model, that will result in an intensive use of RAM, which will be the bottleneck of training the model. Also, the HAODE-Net we used for dehazing has a low accuracy on our training set, which will limit the overall performance of our model.
And multitask learning with knowledge distillation is another proposed scheme of ours to deal with the dataset limitation problem. And the idea of knowledge distillation was initially proposed by Geoffrey Hinton to compress the model using a sort of teacher-student paradigm. Here, we slightly deviate from the initial purposes of knowledge distillation and try to use a teacher image dehazer to distill the knowledge of how to dehaze an image into the dehazing branch of our network. So here, in our case, instead of computing the dehazing loss against the ground truth clear images, which are obviously missing in our dataset, we compute them against the soft targets generated by the teacher model.
We evaluated our results on RTTS, which consists of hazy image with bounding box information for 5 classes of objects. We compared the accuracy of our model with 3 kinds of baseline models: SSD, SSD with dehazers, and fine-tuned SSD. As shown in the table, our model outperforms other models in most classes, and with more iterations to train, the model can be further improved. From the matrices, we can see that our model does improve the accuracy of object detection in hazy environment.
We also discussed the possibility of parameterized dehazing mechanisms. We introduced this hyperparameter beta, which controls the dehazing strengths of the preprocessing module. The best output of different filters is combined with non-maximum suppression, which is further used for downstream tasks.